in the first lecture, we started speaking about feature extraction, and we went into that a little bit, and now we're going to go into it a fair bit deeper. So, whoops. Did not clean up my slides. All right, so input space X. So we had no assumptions on the input space X generically, but all the methods we've discussed, ridge regression, lasso regression, support vector machine, the input space is RD, right? So if you have these arbitrary original inputs, DNA sequences, sound recordings, images, text files, we need to map it to RD, right? This is the thing we showed in lecture 1. And that process is called feature extraction. You could think of a feature extraction function, phi of x, mapping from some arbitrary space X to some nice RD, real dimensional vector space, dimension D. And we mentioned, I believe, feature templates, but let's review that because now we're starting to get into actual implementation. So for this email address task, for instance, that we discussed, here are a list of a few features. And we can define a feature template, which is a group of features all computed in a similar way. So an example would be like a feature that's length is greater than x, where x ranges from 1 to 100. Right? So that's 100 features. Length is greater than 1, yes or no. Length is greater than 2, yes or no. Length, okay, et cetera. And each of those is a separate input dimension, coordinate of your input vector, a separate feature. And well, you can imagine if you were actually to implement all those features, you might just write one function that does them all. It would generate, the representation of the input for these features all at once, all the different lengths, yes or no. Similarly, last 3 characters equals blank, blank, blank. So that would be all however many combinations of 3 characters there are, and each of those would be a feature, and we would have, remember, a one-hot encoding where one of those would be 1 and the rest would be 0, capturing the last 3 letters. So feature template is just a nice idea to have in mind, that it's just kind of one function that could mass produce a whole bunch of related features all at once. Okay. And kind of the theme of today is kind of think less and have the computer do more for you. So instead of trying to brainstorm all the last 3 character combinations that might be useful, make a feature for all of them. So don't think, OK, com.edu, .net, just like make a feature for all of them, and that's a lot, but you have a feature template that does it very systematically. OK. And now that we've spoken about regularization, I can say that so any concerns about overfitting or dimension being bigger than the number of data points, those are all handled nicely with our regularization techniques, L1 and L2. Okay. All right. One-hot encoding, I think you'll recall that. A set of features, exactly one of which is 1 and the rest are 0. Okay. So now we get to some new material here. So how do you represent a feature vector? So what we wrote was kind of very symbolically the name of a feature and then the numeric value corresponding to that feature. Some of them are 1s and 0s, and some are some intermediate value. So the most natural thing, and what we've done in the homework so far, is an array representation, where every feature corresponds to a particular entry in a feature vector. So the first coordinate of this feature vector is 0.85. Fraction of alpha numeric characters, that corresponds to the first position in this vector. So there's a correspondence between each of the d dimensions and each of these features. But there's an alternative representation using a map, or like in Python, it'd be a dictionary. And there you have a key value system where you have the name of the feature is the key, and the value would be the feature value. And the advantages of this representation are when you have a lot of feature values that are 0, because you can have a convention that any feature values that are 0, you just leave out of the map entirely. Right? So if you have a one-hot encoding that has 100,000 possible, a category with 100,000 possible category values, so the one-hot encoding over those category values will always have exactly one and the rest 0. And rather than having to have 100,000 dimensions in your feature vector to capture that one-hot encoding, you can use a sparse encoding and only have the name of the one feature that is non-zero, and the value would be 1 typically. Is that clear? So this is a, yeah.
But that's for the communication purpose. For the real, if you run into the model, you still need to represent that into the array.
So the question is, okay, that's nice for representing, but when you actually run your model, don't you need to represent it in this way as an array? Well, you don't if you implement your machine learning algorithm to directly use maps, and people do that. So in fact, that's almost more standard these days for things like linear models, interestingly. It's because people have a tendency to use massive feature spaces now. So this key value store is actually more common for production software. I don't want to say more or less common. I'll say it is very common. I don't know if it's more common. All right. Yes?
So how do you scale the sparse representation?
How do you scale the sparse representation? I'm not sure I understand the question.
I mean, like, if you scale, like, those 0 would become non-zero, right? So it become non-zero.
Oh, so what does it mean? You mean to transform if you have a sparse vector. So scaling usually means multiplying everything by a constant, which would maintain the sparsity. Anything at 0 would stay 0. But if you add an offset to it, that will make it non-sparse. That's true. Is that what you have in mind?
Yeah, so those scaling are doing homework in math.
Subtract by mean.
Say again?
The scaling, I think we subtracted by the mean, and then no, we subtracted.
Oh, sorry. Okay, you're talking. Oh, I think you're talking about feature normalization, feature standardization. Got it. Great question. Can you propose a method that would allow us to kind of rescale but maintain sparsity? So it's not the rescaling, it's the centering that's the issue, right? It's more the centering. So what you could do, although I don't know if this is done, but anyway, you could have for every vector an offset that says, I want to add C to every value of this feature. So anything that's not present is implicitly C, because C is your offset. I don't think that becomes necessary, though. All right. So arrays are nice because you have, it allows fast implementation. If your arrays are dense and you have most of the entries filled anyway, then there's not much faster you can do on a computer than work with arrays. I mean, you could also plug them into GPUs, which are kind of the cutting edge hardware for machine learning these days. They're very efficient in terms of space also, if it's a dense feature vector. But if your feature vectors are extremely sparse, like fewer than 1% are non-zeros, then the map becomes much more efficient because they take up so much less space. You have so many fewer entries to deal with. Anyway, here's an example, just some actual Python code for creating this is I guess a feature template in some sense. So this is for the ends with last 3 characters. So this actually creates the key value pair that you would need. So it makes a little string ends with. That's part of the key to specify what type of feature it is. It extracts the last 3 characters of your string x, concatenates them together. So that becomes the key in your dictionary. And the value of that feature is 1. So example string, for instance, with this feature encoding would produce a key of ends with _ing, because indeed the string ends with ing. And the feature value would be 1. dealing with you have to recode all your algorithms. Dealing with hash tables is, taking the inner product between two hash tables is a lot more complicated than inner product between two arrays. So there's some trade-off. The overhead's a lot higher. It's just how much are you gaining with the sparsity. Okay. Now we turn to probably one of the more important aspects of feature engineering, which is how do you make linear methods useful in a nonlinear world? You know the limitations of a linear model. You can only find, you can only make predictions that are some linear function of your input vector. So that means if you want to handle you want to make a prediction function that's nonlinear in your input, you're going to have to put those nonlinearities in yourself. So we're going to talk about our different ways to put in these nonlinearities and what you might want to look out for. Okay. So the general philosophy, again, is extract every feature that might be relevant and think less, have the computer do more. That's kind of a machine learning philosophy. So let's think about the predicting health problem. So features for medical diagnosis like height, weight, body temperature, blood pressure, etc. And you can encode all of those things as just numbers directly. But for a linear predictor, it's really important how those features are encoded, because the linear model can't do much with those features it can't do anything with those features besides combine them linearly. So here's some specific nonlinearities issues we're going to talk about. So non-monotonicity, saturation, and feature interaction. Those are our big three. So first, a person's temperature. So you take their temperature, right? It's a health indicator. So if we just fed in temperature as a feature to a linear model, does this have a chance of working well? So yeah.
Just one question. When you say linear model, in the model sense, it's a linear function of the parameter, or it's a linear function of x here?
Yeah. So the question is, what do I mean by linear? And what I mean by linear is linear in your feature vector.
Here you mean linear but when you say the linear model, for example, it means the linear combination of, because...
Yeah, when I say linear model, I always mean that the score function, the key piece of it, is a linear combination of your feature vector. So at the core, you have a W transpose phi of x, where phi is your feature vector.
Still referenced as a linear function of feature.
Linear function of the feature, that's right.
Because the solution actually depends on we use the property that is a linear function of W here. You can see a linear combination of W feature or linear combination of...
Yeah, it's a linear function both of W and of the feature vector. And as you think of it, yeah, either way. But the key point is linear function of the feature vector. Yeah. All right, so linear function of temperature of x. One is just our bias term. All right, so what are the issues here? Here's temperature. And if this is health, we know that
98 is good, 96 is bad, 100 is bad.
Yeah, 98, this is good, very high. And I don't know close by if it's good or bad, but I know that really cold is bad and really hot's bad. And so you cannot fit this with the linear function. That's the issue. So this is, a linear function is monotone, among other things. So it always increases as you move. It either increases or it decreases or it stays constant as you move from left to right for a particular variable. It can't change direction. So anytime you have something that's bad, good, bad, or good, bad, good, it's nonlinear. So you're going to have to do something. So here's an approach. What you suggested, essentially. So, okay, we did Celsius here. So Google, what's Celsius for 98.6? And that tells you the average, the healthy temperature. And you can look at deviations from that temperature and make that a feature. And that seems reasonable. But it's a little, it's like harkens back to expert systems where you have to know something about the world. And would there be is there a way to do this without kind of Googling the healthy temperature for a person? And so you can more generically just put in an extra monomial in this case, an extra transformation of temperature, such that now with a linear combination of these three features, we could, if we wanted to, reproduce this feature. You could expand temperature minus 37 squared, and we're only going to have linear combinations of these terms. And so in some sense, the span of these feature vectors, what you can come up with linear combinations, contains this hand-engineered feature. And I would claim that this is preferred because this is also more flexible. You could use the same model for temperatures of different animals, for instance. But the point is it's more flexible to and easier to use this feature set. All right. So a general rule, you should think of features as the building blocks that can be pieced together in an effective way, linearly in this case. All right. So another example of nonlinearity, saturation. So here, suppose there's some query, some fixed query, whatever it is, and you need to return search results, and you need to rank them, or just decide the probability that it would be a search result that's interesting to the person. So for each product X, say it's Amazon searching, the action is to produce a score for the relevance of X to a particular query. And you might think, I would think that a useful feature in that case would be the number of people who have bought product X, right? It's kind of some generic popularity score. So if this were a linear model, the only kind of dependence we can have on nx is linear. And what that would imply is that our relevance score for a product X when we look at two products, suppose one has 10 people who bought it. The other has 100 people who bought it. A linear model will only be able to make the relevance of the 100-person product 10 times more relevant than the 10-person product. And if 1,000 people bought it, that would be, no matter what, your linear function will have kind of 1,000, will give a score 1,000 times higher than the product. If it went from 10 to 10,000, it'd be like 1,000 times more relevant. So this feels like too extreme a dependence on size. So this is we call this the saturation issue, where, yeah, more is better, but to a point, right? So 5 million is a popular product. If it's 50 million, it's not necessarily 10 times more appropriate to your query, right? So that's the issue with the saturation. And so what are some ideas on how to handle this one?
The log.
Okay, you could transform n of x with, for instance, a logarithmic transform. So what does logarithm do?
It slows it down.
It slows it down. Logarithm, yeah, maybe it looks linear for small values of x, but it levels off. It doesn't completely level off, but it very much slows and decreases as x gets larger. Great. So that would be a way to transform it. Yeah. You can use a sigmoid. So what's one issue with logarithm? It's not relevant to this case, but in other cases that you have,
If it's negative.
yeah, it has to be non-negative. That's right. So logarithm has to be non-negative. A sigmoid function, though, maybe it looks like this.
It's not.
So this can handle non-negative. So what's an example of a sigmoid function? A sigmoid describes the shape of a function. It looks kind of S-shaped like this. So what?
Tan x by x.
Yeah, right. The inverse, the CDF of a normal distribution would be a sigmoid. Great. Arctangent. Great. The logistic loss that we talked about. Great. Okay. Not arctangent. Oh, hyperbolic tangent? Hyperbolic tangent is also.
It's tan x by x or something like that.
Okay, anyways, different transformations we can do. The different properties. Logarithm keeps increasing. A lot of sigmoids have limits. They can be bounded between 0 and 1 or negative 1 and 1.
Is it a problem that sigmoid is not convex?
That's a good question. So is it a problem if we transform our feature vector, if we transform a particular feature with a function that's not convex, does this cause us problems? You think no, why not?
Because after you transform, it's just a number.
Because after you transform it, it's just a number. Right. There's no, the non-convexity of phi of x never shows up in our objective function because we only deal with the output of phi of x. We never have to push back into the function itself. If we are optimizing over the nonlinear transformation phi, not nonlinear, the non-convex transformation phi, if we had a sigmoid, but we parameterized it in some way that was dependent in a non-convex way on some parameter, that would be an issue. That's what happens in neural networks. But here, it's a fixed transformation, and it's OK.
So how do we interpret the sigmoid over here in this example? Like, say you get some numbers between -1 and +1, right? So is it kind of your...
So how do you interpret the transformed number? I think the point is that you don't need to interpret the transformed number. What you can, or one way to interpret it would be to kind of invert the transformation and imagine that, well, let me not say invert, sorry. So it's just as though you had written down a function of the form, say, w0 plus w1 log x instead of w1x. It's just changing the function that you're trying to fit. That's the interpretation.
Can you categorize it? Set it in a bucket?
So another proposal, independent of logarithm. Discretize x, put it into a bucket. Great, I like that suggestion a lot. OK. So here's your log transform idea. Great. OK, quick question. I'll come to the discretization in a second. Does it matter what base we use in the log? It doesn't, because the logs of different bases are related by a linear, by a scalar factor. And so, well, there's one potential issue. So it would only need to have a different coefficient to, you can achieve the exact same functions. The only possible issue is that different log bases may lead to different magnitudes of that feature. So if we're doing as we should and rescaling our features, then it doesn't make a difference at all. If we're not, then there's some scale differences in the output from logs with different bases. All right, now here's Joy's idea. What if we do a discretization? And so here we've made 1, 2, 3 features to represent numbers. And it's by buckets. So if the number shows up between 5 and 10, this is 1, and the rest are 0. Between 10 and 100, that's 1, and the other 2 are 0. And it's at least 100, then that one's 1, and the other 2 are 0. That's a very standard approach. Yeah.
But how do you know, like, what?
How do you know where to make the cuts? Well, your guess is as good as mine. But there's some standard things you could do. Like one obvious thing to try is take some quantiles. So take your training set, look at all the values for a particular feature, break it up into equal bins based on counts of items in the bin as opposed to the values of the items themselves. So that way, if your distribution of values is like really heavy here and then has a long tail, so there's kind of 2 extreme things you could do. One is you could take the range of the value and divide that up equally. And then what you'll have is a whole bunch of bins that are almost empty and some bins that are really full. That may be good, that may not be good. Another thing you could do, kind of another extreme, is divide up so that each of your bins has the same or roughly the same number of items. So that'd be kind of more of a quantile approach. There's kind of two extremes.
So what you're saying is basically we can plot a histogram type of thing and give a bucket size, like 100 or 10, and then see how it looks, right? And if it has a fat tail, like that, then do something.
Yeah. So the basic, yes, you can look at your data and use your intuition on what would be what's useful to extract. Maybe all your data is here, but maybe all the interesting predictive power is here. And maybe it really matters if you're here or here. And in that case, it would make sense to break this up. But if kind of all of these are outliers and almost irrelevant, group them. And maybe all the interesting stuff is happening here. So if you kind of don't know the right approach, you have to try different approaches. But there's one issue which we've touched on here, which is for the tail. So the bins that don't have many entries. Let's suppose we're doing some regularized linear model, which is the only types of linear models we should really be doing. So suppose we have an L2 regularization and a linear model, and we have a bin that has very few items in it. What will happen to the coefficient corresponding to that bin, so the parameter corresponding to that bin? Do we have any idea? You think 0? Yeah. Why do you think 0?
Well, the coefficient is really not going to help you improve the prediction because it's not totally data points that you can improve, but because they're kind of the same parameters as the other coefficient.
Yeah. Yeah, I agree. So the suggestion is that you have your objective function, right? And you're trying to maximize the average performance across all your data. And there's these two data points, say, that have a non-zero value for this one particular parameter. So you can imagine that improving your performance on those two values will have almost no effect on your overall objective function. But if you're regularizing, if you make the parameter corresponding to that rare bucket non-zero, you're immediately incurring some regularization penalty. And yet, as we kind of just said, it doesn't help you hardly at all decreasing your average loss because it's so few points that are ever in that bucket. And so the effect would be that the parameter corresponding to that bucket will be really, really small because of regularization, kind of the regularization penalty outweighing the benefit of making that non-zero. So, okay. So if we have a rare bucket, we're going to expect the coefficient to be really small or non-zero. So so is that an issue?
Yeah, you're essentially kind of assuming that beyond that point, very large numbers is actually not that relevant, which is kind of counterintuitive.
Yeah. So, like for instance, suppose we didn't do our bucketing very well. And like this was very rare and this one was very rare. So both of these are going to end up being 0, or the parameters will be 0 or very small. And so in some sense, with regard to this feature, the very large and the medium large will have the same will have the same effect, which is to say 0 input from this feature. So you could the parameter values might be like large, 0, medium, small, 0, just because these buckets are very small, whereas you might really want a more smooth dependence in that feature. So because of that, I often like these one-sided buckets, where instead of bounding, it's supposed to disjoint intervals, we have nested intervals. So first is greater than or equal to 5, the next is greater than or equal to 10, and the next is greater than or equal to 100. So what happens there is that, so this guy, for instance, an input example that's in this bucket will also be in this bucket and also be in this bucket. So if there's very few items in this bucket, okay, the parameter corresponding to this bucket will be 0. But it can still benefit from being in this bucket and this bucket. So the intuition is that what we're doing for guys that are in this bucket should be similar to the ones in the neighboring buckets. And if the parameter for this bucket is very small because there's not very many items in it, it'll kind of default to whatever happens to these other buckets. Yeah?
If you were using sigmoid functions, would you want to do a similar thing where you had multiple ones that picked up at different points so you get a similar effect?
Oh, interesting. So you're suggesting basically a third approach, which is multiple nonlinear transformations may be shifted. Is that right? Nonlinear smooth transformations, like a sigmoid or something.
Because with sigmoid, it's kind of like a smooth bucketing in a sense.
Yeah.
You only have one.
I like it. I like it.
If you pick the wrong one, you're going to have no information if most of your points are way out either end.
Great. So I think usually you would do a sigmoid that has a nice slow slope in the middle. But eventually they're going to saturate. And if you've done it poorly and there's a lot of action going on in the saturation points, then you're not getting a lot of information. So yeah, I really like the idea of shifting your sigmoid repeatedly.
Or you can just parameterize the sigmoid so that you can tune the parameter so that you might want to figure out how much the slope should be.
Okay, so have a hyperparameter that you tune. Okay, sure, you can absolutely tune your features. And in this case, you're suggesting a fairly unique situation where you have a smooth parameterization of your features.
Okay. Yeah, so essentially in order to determine, rather than having to blindly pick which sigmoid you want to choose, you can then say, based on this hyperparameter, choose the best sigmoid that will transform this data.
Right, so you can, and interestingly, this is basically what a neural network does, where these sigmoid transformations are parameterized as part of the full objective function. So you guys basically reinvented multi-layer perceptron, which is pretty awesome. So I think we could skip week 5 or 6. This is week 5. All right. Okay. This was our one-sided bucket idea. I find it useful. All right. Interactions. This is, all right, so a classic thing in statistics is given someone's height, predict someone's weight, given someone's weight, predict someone's height. And I guess the standard thing is you get ranges for a given height, what the healthy range of weight is, and these sorts of normative ideas. Anyway, suppose we wanted to make such a model. The idea is you can't just look at height or weight in isolation and come up with healthy or not, because there's some relationship. Larger height would suggest a larger healthy weight. So it's relative. You might think like, oh, it's the ratio of weight to height that's important, or something like that. And so you could enter ratio of weight to height as a feature, as a new feature. But you can also just directly add in, okay, let me skip ahead. You can directly add in an interaction by multiplying height and weight together. But okay, so let's work through my little derivation here. So you could Google what's the ideal weight from a given height, and you find this, this formula someone has come up with. And you can look for, as we thought about previously, the square deviation between the predicted optimal and the actual weight for the given height. So that would be kind of a hand-created prediction function. And you can expand this out, and you find that this thing is a polynomial of degree 2 in h and w. And you have this interaction term, hw, and squares of w's, and linear terms of w. And now, given our let's be minimalist approach, and let's create building blocks, the right approach is clear, that you just want to take these individual monomials as features. And now it can reinvent what the normal relationship is between height and weight in a population, using these as our features. And it might rediscover this, or it might not. But it's more flexible. Okay. Any questions so far? All right, so next, this is a light slide. It's just some terminology. There's something called a predicate. So it's used, so a predicate is a feature that's true or false, in a sense. It's something that answers a question about the input. So, for example, a feature might be, for X, is the subject sleeping, yes or no? Right? So it's 1 if the subject is sleeping, 0 if it's not. This could be like someone's videoing a car going by. Another feature, is the subject driving, yes or no? Right? So these are predicates because they're answering some question about the input. And then an interaction of predicates would be subject is sleeping and subject is driving. It's like and it turns out that you can represent that by multiplying these two features together. So if you multiply these indicator functions, that's the same as kind of the conjunction of the statements. All right, so from the question earlier, so what's linear? This is our hypothesis space, our linear hypothesis space. And so is it linear in W in the parameters? Yes. Is it linear in the feature vector? Yes. Is it linear in the original input space? No, it doesn't even make sense, really, because X is not. And to talk about linearity, you need like a vector space. You need vectors you can add together. You have to define addition and scalar multiplication. And there's no vector addition defined for MP3 files, right? Or DNA sequences. So linear in X is not even is well defined. Okay. And so there's another term which is expressivity, because I want to say something like having a nonlinear f of x is important for expressivity. This means like remember we had the set of all possible prediction functions where our Bayes prediction function lived, and then from that we chose the hypothesis space, a subset. So linear functions are kind of, there's only so expressive, so complicated a function you can produce with the linear dependence on phi of x for fixed phi, for instance. And so by going nonlinear, you can have much more complicated expressions in terms of the original x with nonlinear features. Okay. All right, so here's an example. Input space x1, x2. The two classes are the two colors. The circle is one color. The non-circle is another color. And so what kind of feature can we engineer to make these two classes linearly separable? So to find a linear function of the input or of the feature. So the original feature space may be just x1 and x2, the input coordinates. We want to add another feature to that feature representation so that we could have a linear function. Yeah?
And take the polar coordinates.
Okay, so one suggestion is make a feature that's the distance from a point to the origin. So if you know this is 0, 0, you're in good shape. I don't know if it would work so well if the origin were here, though. But OK.
We can take the.
If you know where the sensor is, then you can certainly do that, yeah. What would you want the decision boundary to be? A circle. Right. So let's think this through for a second. This is a classification problem, so let's think in terms of making a score function, right? And for score functions for classification, a positive score is like a positive class, and a negative score is a negative class. So we want a score function. What's the input space for the score function here? Original one? x1, x2, R2. That's the original input space for our score function. And we want it to be either negative here and positive here, or positive here and negative here. So we want something that looks like it could, for instance, be like a cone that starts negative in the middle and then gets bigger and crosses 0 at this boundary and then continues. So we need a function of x1 and x2 that looks like that.
So we need a polynomial of degree 2 in x1 and x2. So have x1 squared, x2 squared, and x1, x2, but maybe some relationship between x1 squared and x2 squared.
Sorry, I didn't hear. So we need a polynomial of degree 2. We need all the monomials of degree 2 between x1 and x2.
Not necessarily all of them. I mean, I was thinking more in the form of, if you are thinking of a parabola, whatever. Essentially, whatever terms we end up, if we write that expression further, we can take a look at that and say we'll get x1, x2 separately. I think we get x1, x2 as well as a combination.
What if we thought in terms of level sets of our prediction function? So if our prediction function is f of x1 and x2, so one possible set of level sets would be circles, right? If the level sets were circles, we'd want the 0 level set to be this circle and the 1 level set to be this circle. So to get level sets of a function that are circles, we'd need like, so for f x1, x2 equals some constant c, and that, what's the formula for a circle? x1 minus x1, 0 squared, or some radius squared, plus x2 minus x2, 0 squared. This is r1, r2. This is an ellipse, actually. Like the same. That's circle. Great. All right. So this is the expression for, this is the equation for a circle. And so if f of x1, x2 were equal to this function, then the level sets would indeed be circles. Okay, that's good. And so we could multiply this out and see what features we need, what functions, what nonlinear functions of x1 and x2 show up in that linear combination. All right. So if we just put in x1 squared plus x2 squared, it turns out that's sufficient. Just video. It's kind of cool. So this is a video of transforming this feature space. So here's the original feature space, x1, x2. This is the decision boundary that we want. Okay, so the blue and the red points. And then they're going to add in this extra feature in the third dimension. And then you can see that now the red points are separated from the blue points by a hyperplane that goes through there. Yeah, that hyperplane. Cool. OK. All right. So that's all I wanted to say about features. Well, here's one last point, which ties it together with our hypothesis space picture from the first lecture. So if this big ellipse is a set of all prediction functions, right, and F is our hypothesis space, now let's call it a linear hypothesis space. So let's forget about regularization. Now, regularization is another way to grow or shrink a linear hypothesis space. But unregularized is as big as a linear hypothesis space can be. So suppose this is F, and I suppose it's an unregularized set of affine functions on a set of features. So how can we make this hypothesis space more expressive, larger? This is as a function of input x, the raw input x. Yeah, so by adding more features, we can potentially make this space of functions of x now larger. Okay, so it's still a linear function of some feature vector, but as a function of x, it's a larger space of functions. We can, in the previous example, we went from, we can now represent this kind of circular decision boundary, whereas before we could only represent linear decision boundaries. Cool. All right. Question, yeah.
So if for one sample we have, for a feature we have the same value, does that mean that it basically has no contribution to the?
Yeah, so if a feature doesn't vary across all of the data points, yeah, then it gives no information.
So
you can drop it, yeah. Yeah.
I guess this is obvious, but essentially we'll have to look at the data, understand the data to be able to extract the type of features we want, right? So what I was trying to get to is figuring out what features you need does need understanding of the data, but we don't want to make the features way too domain specific, as in, like, we don't want to have special rules, like maybe look up a formula that had, for example, for temperature, we don't want to say something like, something minus 37 square or something like that. But just, is it that you try to look at the data and then see how you can best manipulate this in a way that a linear model is going to be happy with it, and then come up with all these various transformations so that you get more enhanced feature vector?
Yeah, I think the idea, so the comment is that it seems like there's some mix of looking at your data and trying to use your knowledge or intuition on a good way to transform the feature, the original inputs. But then I was kind of saying, all right, but you don't want to invest too much into finding like the perfect feature. And the reason is, it's not that human intelligence isn't really useful for coming up with great features. It's that there's a certain kind of, to a certain extent, the linear model doesn't care if you found the perfect intercept, like 38 in your new feature x minus 38 squared or something, because it's going to be able to figure that out on its own. So there's a certain amount of feature engineering that's irrelevant, more or less, to the model. And so don't bother and spend your time doing something else and keep it simple. But linear models can invent their own nonlinear transformations. So maybe it's worth doing the research of whether logarithm is better than square root or better than sigmoid, because linear can't, if you give it log and you need square root, it's out of luck. So that would be a point where a human needs to do some work.
So what if instead of trying to figure that out, you throw in all those features and see which one it rewards more weightage to?
Yeah, so can you just throw in all those transformations and just see what works? Yeah, I like that. That's a good approach. That's a good approach as long as you have a decent amount of data. Yeah.
And you regularize.
Always regularize. It's not machine learning without regularization.
It's more of a comment really than a question, but this seems to be really common practice. I've definitely done this as well, but it feels kind of sneaky that we get to like pick these nonlinear functions like log or square root and do this like pre-processing step where we apply those and then once we're done, we get to like use all these really nice linear methods afterwards. It's so convenient that and then we don't have to answer any of these questions about convexity and those things. We're like, it's like a nice world. All we have to do is make sure that we transform by the right.
Yeah. So you're very free to transform however you like, but it's a responsibility too, because the transforms you don't put in, you're never going to get with a linear model. Yeah. But yeah, linear models are nice for that reason.
So on the board, you kind of visualize that quantile and like a function of linear. So now, if your data is like sort of two-dimensional, how do you sort of visualize like the subspace of like let's say it's a
yeah. So I was just so the comment is we are visualizing one input dimension at a time and thinking about transformations, and you're kind of suggesting, well, what if the natural transformation involves looking at two of them at the time? So this is this is kind of taking two things together: the issue of interaction and the issue of non-linear kind of effect of each input dimension. I mean, in some sense, you have the same set of tools. You could use a nonlinear transformation on two variables, but you have to figure out what that should be. You could histogram in 2 dimensions, or come up with buckets in 2 dimensions. It's just that they're going to be, the number of those will grow much more quickly because you have to cover a 2-dimensional space. But yeah, those are good questions.
Are there potential concerns with correlated sort of engineered features and how that affects regularization?
So are there concerns with you do all this engineering and you end up with very correlated random variables? So So how does our discussion about correlated random variables from the regularization play in? So I guess, what would the concern be? That by adding more correlated random variables, you will end up with prediction functions that don't do as well, is the worry?
Yes, I'm trying to remember how they're different regularization.
Right, so let's rehearse that. So if you have, so first of all, we've rescaled all the features that they're the same scale, so center and scale them. So for correlated random variables, L2 regularization likes to split the weight evenly among correlated random variables with the same scale. L1 doesn't care where it puts the weights. And so you can kind of end up with, just depending on the randomness in the data, you might end up with all the weight on one variable or some arbitrary mix of some other ones. There's no preference with how the weight gets distributed. But then, so a lot of times people will do a combination of the two, the elastic net. And that tends to spread weight fairly evenly among correlated random variables. But that'll also drive variables to 0 if it doesn't seem relevant. So there are other perhaps optimization issues with correlated random variables. So it might make your objective function kind of have a very narrow valley, which is not conducive to our gradient methods. There could be issues in that way. But I think statistically, we're in good shape. Yeah. So some people whiten their data, so they kind of, it's kind of you can kind of thinking about it as transforming your input dimensions into some new representation, into some new basis, so that your kind of feature vectors are orthogonal.
This is just a comment to kind of expand upon what you said earlier. But so I was just thinking about, so it's like when we have what we're doing when we add these extra features is it's kind of like not cheating in a sense, but in the sense that we're adding more dimensions to make a problem that initially was like lower dimension but non-linear. You're just adding these extra dimensions which hide the non-linearity, but then in this extra dimensional, higher dimensional space, you can use a linear model.
Okay, so let me rephrase that. You're saying that if you suppose our original representation was a vector for convenience, and so imagine like the Bayes optimal prediction function was some nonlinear function of this input vector, but we've created a new function of the input vector, phi of x, to create a new vector, and the Bayes prediction function is now a linear transformation of this transformed variable. So yeah, that's nice if you know how to invent that featurization that makes the optimal just a linear function of your feature vector. That's the magic of it. And I find it nice to bear in mind the kind of limiting case of this that I mentioned in the first lecture, which is imagine you had a super feature that took your input vector and mapped it to a single number, which is like the correct output. And in that case, the Bayes prediction function in that featurization would just be like the identity, because the feature already solved the problem. So that'd be like a limiting case of that.
Yeah. In terms of cover the non-linearity, usually we do that. We change this feature to non-linear. So in the whole thing, it's a non-linear as a function of x, basically. Is there typical to also nest it in the other way? So put the linear function in the internal, and then nest, have another one non-linear. For example, the classification is apply a sign function on the linear transformation of this thing. Is that also typical, or you?
Oh, I understand the question. Yeah. So the question is, I think I understand the question. So we're doing all this nonlinear transformation on the inputs, on the input vectors or the inputs. What about a nonlinear transformation on the outputs? Is that right? So I think that this is most relevant for regression setting, because if it's just classification 0, 1, there's not really much you can do.
Classification is a sign function applied to that thing, which is sign function is nonlinear.
Okay. So so in our setup, we produce a score function, a real valued number, and then to actually get the final classification, we take the sign of that. That's true. And you're suggesting, could we?
I mean, typically, how popular? You know, are we very popular to do that, or you know, it's almost every case. You know, 90% of the case, we try to feature engineer the nonlinear part into this phi here, instead of bring up another g of x to transform the output.
Right. So I think that the mapping from the score to the classification, that could be parameterized a little bit. You could change a threshold, like not use a threshold of 0. So there's a little bit of play you can get there, but not a lot. Well, you could have a non-monotonic transformation. Yeah, I have seen people do that. So let's give an example. So you've learned a score function. This is like your input space. We'll write it as one-dimensional. And OK, score function, here's 0. And suppose there's some ordering. Suppose it's a one-dimensional input space. And our score function does something like, well, I don't know. So a big spike. OK. All right. So this is our score function as a function of x. So the simple classification would threshold on 0. Now, you're saying, I think you're saying, maybe there's another more complicated transformation we can do of this output to get a better classification. So, and maybe you could learn that even on some new data. So in some sense, you're thinking of, you could think of the output of the score function, you could think of that as like the input to a new prediction problem, where you're trying to map the score to a new score or a class directly. And you could fit that. So perhaps what it will find is that the score is pretty good except for these outliers. And for the outliers, the things that are really high and positive, actually, they're negative. And so maybe it'll learn to flip the sign of the extreme values or something like that. So that could be another layer. That's interesting. But this is more like a two-stage thing. And it's not, so maybe a little bit more analogous to our pre-processing of inputs would be something that's pretty common in regression, which is where you could transform your output values before you do the linear fit. Like take the logarithm of your y's, the square root, or the sigmoid. So that's another way to make things linear, right? Yeah.
Is it common to have your transformation kind of figure out empirically? So suppose that your input space is you take one dimension at a time. When you plot x, y versus x, if it's some function, and that becomes your transformation function.
Sorry, can you say it one more time? What I'm hearing is that you take one input dimension at a time and try to.
So you're trying to basically you're plotting essentially your y is a function of x, and x is basically one dimension, two dimension. And then you can fit a function, let's say the parametric is something else, and this becomes your
features
transformation. Yes.
Okay.
You see people doing it, or is it?
Okay. So the proposal, if I understand it correctly, is you have an original input feature vector, and you make a new prediction problem for each feature vector, for each entry in the feature vector, and you try to predict y given x1, and you make your best prediction function. And you try to predict y given x2 and make your best prediction function. And then you'll have an entire array of predictions for each of your input dimensions. So you go from RD to a new RD, and then the proposal is use that as a feature vector in another model. I've never heard of that. Let me think about that for a second. Let's all think about that for a second. What are the implications of that? Will that work? So what you won't get is interactions. This won't help you get interactions between variables. If the functions you're learning from an individual feature can be nonlinear, you might extract the right nonlinearity, because it is easier to learn a nonlinear function on an input space of just one dimension than like thousands of dimensions. Anyway, it's very interesting. I have not, I don't think I've seen that. Well, yes and no. It's very related to something called a generalized additive model. So a generalized additive model is a function of this form. Okay, so we take each coordinate at a time, one coordinate at a time, and we learn, as part of the learning process, a nonlinear transformation of just this one coordinate. And then we take a linear combination of those. And these are the linear transformation SI, the nonlinear transformation SI, and WI are learned jointly as opposed to two-stage, like you're saying. But this is a very similar, it's the same hypothesis space, essentially, potentially. It depends on the nonlinearities you're allowing. This is called a generalized additive model. I wasn't planning to discuss this, but I might since it's been brought up. It's very related to boosting. And to handle the issue of interactions, you can add in, not a lot because it takes a lot to compute, but you can add in some couples. So you have some nonlinears of 2 at a time. And these nonlinearities could be fit like by making a big set of basis functions over your input space, kind of whatever, like intuitive like Fourier basis or whatever. And then you could fit those actually linearly also. So at the end of the day, you're doing regularized linear fitting even to get this nonlinear transformation. Cool. So yeah.
So what are some disadvantages of solving problems with growing linear model like this, like a bionic feature? Growing.
Disadvantages of continuing to throw in more and more features? That's a fair question. So you can't get something for nothing. You could easily make it. So I encourage people to just make more features. When in doubt, add more features. But eventually it does blur the signal. If you add a lot of meaningless features, what happens is that by chance certain features will seem meaningful, but they're not, and they will look just as meaningful as ones that really are meaningful, and it'll be difficult for the model to pick out the ones that are useful. So, I mean, a lot of machine learning is targeted towards situations where you have huge amounts of data, and in that case, this is combined with regularization is usually not as big of an issue. But in the limit of huge number of features, even with regularization, you won't overfit, but you might drown out all the. Why do I say you won't overfit with regularization? Because you always tune your regularization parameter specifically to not overfit. You'll choose the regularization parameter even if it's extremely high. You'll choose it high enough so that you don't overfit. So overfitting per se is not an issue, but it's possible that you will not fit as well as, you won't fit as well as if you had only had the important features there to begin with. It's just, the question is how much worse are you? Is that clear? Maybe I should say it again. So generally speaking, our regularized linear methods can handle adding lots more features, but there is a gradual cost to it in the sense of if you keep adding useless features, your fit will eventually get worse. But you need to add a lot of bad features to really make it significantly worse.
So that means that you can always grow this hypothesis space.
You can grow the hypothesis space adding features always grows the hypothesis space. The issue, so what happens, so in terms of our approximation error, estimation error, optimization error, let's just do approximation and estimation. Adding more features will decrease approximation error. Approximation error is if you found the best possible function of your new features, all your features, how would you do? But the estimation error is the fact that if you don't have enough data, you're not going to be able to find the right function of those features, and you'll maybe end up with a poor fit using that larger set of features.
Okay. Going back to the example you did in R of overfitting, where you had, you chose
Yes,
a function
the
with
polynomial
points.
fit.
If one of your features was that polynomial, you would pick it, you'd give it 100% weight, but it would fail completely on your validation and test data. I mean, you'd have to try a bunch of crap to end up with that as one of your features. But if the polynomial fit was one of your features, when you then did your linear weights on it, it would get all weight.
So tell me what the, yes, so what you're saying is that if, okay, so so in the example from the first lecture, we had a situation where we had not too many points, maybe 10 points, and we had, I guess, a 9th degree polynomial that interpolated perfectly the points. And you're saying if we had made that polynomial a feature, so then we had this really simple function that puts all the weight on the one feature, and it will get 0 training error, but it will perform terribly out of sample. And so I see. So then maybe this is challenging my claim that all the regularization, you can always regularize your way out of overfitting. But you're still safe, you're just useless here, because when you tune your regularization parameter, you would bring it all the way down to 0. You would make it essentially 0 or something like this. And so you wouldn't overfit, but you would underfit or something like that. But yeah, that's an interesting example to think about.
I mean, in an infinite feature space, you're always going to have one feature that is terrible, it's incredibly overfit your training data.
Yes.
And that would be the one that would get, like, in the limits as you go to an infinite feature space,
Yes.
you are going to overfit.
Or you won't be able to fit. So as you add more and more features, eventually, if you imagine one feature, eventually you can have a single feature that, if you just use that feature, you can overfit your data. Then
if you take it to extreme, if you have all the possible powers of x, you can essentially come up with any polynomial function of x, and a high enough polynomial degree will happily fit every single thing without any error.
Well, so you're saying that if you have all the degrees, then you'll fit.
I mean, just as an example, that in a sense we have infinite features because you have all the degrees of the polynomial. So
There's a little difference between your two examples, though. So Tom's example, there was a single feature that had all the information. In your example, it's spread out among multiple features. And regularization will help much more in your scenario. So it's the one feature that fits your training data perfectly. But this would have to be like an adversarial feature. It's almost impossible. Because if you, we assume that the features are kind of, they shouldn't be generated in a way based on the training data.
So that happens only if you have the label. If you have a feature that's basically the same as the labels.
If you have a feature that's the same as if it's always producing the target function value, which is good, then it's a good feature. But if it's only the same as the labels on the training data, that's terrible. But it also is, if that happens in practice, there's some kind of a mistake, right? This is not, it seems like that would be unlikely to happen on a large data set unless there's something was going wrong.
Yeah, I think that if the data, you have a lot of data, that's basically can avoid overfitting, right? So even the space is larger, but you have more data, you can remove those overfitting functions.
Yeah, with more data, you can reduce your estimation error, find the function that is kind of the best in the class, reduce overfitting. Yeah.
Are there any regularization approaches that would kind of scale the regularization to the complexity of the transformation you've done? So that you would favor, say, an x over an x cubed or an x to the 4 or an, x times y times z or something?
Interesting. So are there any regularizations that, can I generalize to say, penalize different features in your feature vector differently? And then you kind of are suggesting, and could it be somehow automatic so that more complicated feature transformations are penalized more?
At the time that you're doing the transformation, you can also scale appropriately. So if it's something that's like a 4th order thing, you make the weights, you make it
higher. The regularization, yeah. So I think you're asking, do people ever kind of regularize different parameters differently based on your knowledge of kind of how complicated that feature was or something? Or even, so you could do that. You could phrase it differently and put it more in terms of, you could regularize differentially depending on your prior belief on which features will be more useful. You're like, and what's the difference, right? If you think x to the 4th is actually really useful, why would you penalize that more just because it's x to the 4th? X to the 4th could be the right thing, right? So a default might be, yes, higher power, regularize it more. But maybe you have some knowledge, and maybe you should regularize respecting your knowledge and regularize more strongly when you're like, I don't think that's so useful, but I'm going to throw it in just in case, but I don't want to overfit, so I'm going to regularize it pretty heavily. And if you think x to the 8th is the key, then regularize that very little. This is getting towards Bayesian statistics, Bayesian methods, where you kind of, in a Bayesian method, you have something that's called a prior distribution, which essentially assigns weight to all of the prediction functions you might use in advance before you see any data. And so the application of that often is, you could see that as showing up as differential regularization on different features.
Yeah.
Or rather than regularizing the different features ex ante, could you use like some information criterion like AIC or something ex post to punish more complex models? Like, isn't that what those are invented for? Was you would cap something at R4, cap it at R6, and then you're saying like if the R6 one's going to win, then it has to like overcome the additional complexity of having many more features.
All right, so I think what we've kind of popped up to the next level, which is if someone proposes maybe multiple prediction functions, each from kind of an increasingly complex sequence of hypothesis spaces, is there some way to penalize your choice so that even though the more complicated one fits better, you're less likely to choose it because you're penalized for the complexity of the space? And there are many techniques like that. You mentioned AIC and BIC. There's minimum description length. There's different things. But we have a much more practical approach than any of those, which is how does it do on validation data, which is really, it's more directly the bottom line. Now, if you don't have enough data, you might need some of those other. So the AIC, BIC approaches, there is no validation data. This is purely on training data. And so if you have very little data, maybe something like that is recommended. But kind of machine learning scenarios, you usually assume you have enough for a healthy validation set, and so you can select in that way.